1.7, so it's close to that, or 0.17 rather. How long should the cart's motion last? Well, it's going to start at 0, and this guy's done at 10, and we don't move at all to begin with, so maybe that's a 0.5. That's like 9.5 seconds, if I'm getting really, really accurate here, or precise. The whole thing is 10 seconds, but we're not moving for the first 0.5. When you're ready, hold the cart in front of the sensor. When everything's ready, start recording the data. Go ahead and see if you can match these things up. And of course, they're going to say, go ahead and do it. When they tried it and they felt confident enough to publish it, they got 5. So I don't know. Let's see how well we can do. So it doesn't really matter where I do it. I don't want to do it right up top because I can't go closer. But it doesn't tell us where it starts. It just tells us whether it's moving or not. So we're not moving at all to begin with. It's 0 to start with. So I'm going to start up here again. I don't know, maybe around 60. And then what I want to do is to practice this, I'm supposed to stay put, and then I'm supposed to move close at a constant velocity. And we're going to be learning in a little bit, constant velocity. It means a change of velocity. This slope is acceleration. So we're going to constantly speed up and accelerate. And then we're going to move back. Let me see what I can do. I don't know. I can't tell. Now I'm going to push this button and see if I can get this guy going here. So let me push the button with my left hand here. And here we go. Oh, I should have gone. And then back here, back, and then back, and then down, and then back. I wasn't even paying attention. And then, yeah, fantastic. Wow, how'd I do? They got 5.1. I got 5.6. A higher score is bad. Is worse. It's like golf. Lower is better. So I didn't do very good. I was talking at the same time. Maybe I can defend myself and come back and do this again. But if you look at, I need to look at the graph, but I want you to look at this. I'm going to see if I can't put the camera towards this guy while I look at the graph. I'm probably going to make myself cross-eyed doing it, but here we go. Let's go. Let's see what we got. So I'm down, and then I'm back too far, and then back too far down. This is difficult. And then back, and then, screw it. Done. So I was moving all over the place, and it turns out it's this blue line here, and I did even really worse. I did really worse. It's 8, okay? 8.046, okay? So, yeah, should I stay here for a long time and practice this? Maybe if I want bragging rights to get a low score. But I really don't see how that's sort of helpful. One of the takeaways for this when we do this every year is that looking at this graph, sure, you can figure it out, but it turns out that we as humans, when we look at a quantity versus time, and now we're looking at a quantity versus time, it really complicates things very, very quickly, at least for me. Maybe if you got in here, you could do it perfectly really, really quick. But what I'm really looking at is a plot of meters per second and then divided by seconds. So it's sort of a it's not very cut and dry. It's not very easy to do. It's a much more complex motion by looking at this thing here. So let me see if I can get this data over here and see what we got. So this is page 10. So page 11. For your best attempt, how well did the cart's plot of motion fit the plot that was already in the graph? It was crap. Crap. That's a science word. It was crap. My score was 5.610. Their score was crap too. That's fine. Again, they don't ask us any other information like, hey, we're going to analyze this, and then it's just all over the place. And you could see how sensitive it was. If all I did was just move things all over the place, you can see how it goes. I can do this one more time, not trying to match it, just to show you how sensitive this is to moving around. I'll start it, and you can see it's. This is just me moving it back and forth. You can see it. I got a nice little sine wave here. Back, forth, back, forth. That's trigonometry. That's what waves are. Back, forth, back, forth. That's beautiful, but it's not what it's not asking me what I was supposed to do. I got a fantastic score of 20. That's awesome. I'm really proud of that one. I'm gonna go write my mom. So yeah, let's keep on going here. Let's finish this up. So we have one more to do. I know that we did 1 and 2. And now we're doing 4, so it's not as if we're not doing number 3. So not a problem, we're not missing anything. Open activity. No, you don't need to save it, but thank you for asking. I'd like to do 4 and open up. There we go. There is the About page. It's fantastic. This time around, if I go ahead and look at this thing, we are going to get 3 graphs. So we had 1 graph each last time, but now we're going to get 3 graphs. I think if I maximize this, I can see all of them. Okay. So you can see, if we look at all 3 of these graphs, all 3 of these graphs have a horizontal axis. This one is time, this one is time, and this one is time. That's cool. They all have the same axis being time, and they all have the same time axis. This is 0, that's 1, that's 1. So they're all sharing. So what we're doing is we're observing this vertical quantity, which is position, and we're observing velocity, and we're observing velocity per second, which is acceleration. We're observing position, velocity, and acceleration all at the same times. Okay, so this data will be over here at 4, will be the position at time 4. The data here will be the velocity this guy is moving at time 4, and this will be the acceleration that this thing is experiencing at time 4. Okay, that's kind of cool. It's all measured by this device here. It's measuring all this distances. We don't need to do anything. All I need to do is just click the stupid mouse. Okay, so let me push a button here. This is page 12. Page 13 is over here. Prediction. Sketch a prediction of the position, velocity, and acceleration versus time graphs for the fan cart's motion. So what we're going to do is this. We're going to start down here, okay? We're going to start at 40 again. I think it even says, please start at 40. Let me see here. Yep, right there it is. Please start at 40 centimeters. There's an older version here that says, please use a string and then stand over there, but obviously we can't stand over there. There's a computer over there, so I'm just going to use my finger to stop it. Start at 40, and then what we're going to do is, this is the motion. We're going to do what I said before. We're going to do the dropping experiment, but we're not going to drop this. We're going to start from 0 and let it speed up that direction. It would be as if we put it at the top of that guy and then let it speed up as it fell back down. Of course, we don't want it to crash into the floor. We'd catch it before crashing into the floor. But we also don't want it to speed up so fast it's hard to see. So this won't speed up as fast. So their question is, if we were to measure the position versus time, what will it look like? If we were to measure the velocity versus time, what would it look like? And if we were to measure the acceleration versus time, what would it look like? And that's what we're going to do. And rather than, I've done this experiment before, so rather than giving it away, I'll just leave that as a discussion point. So when we look at this video together, I'll stop the video. Hello, future me. We're going to stop the video, and we're going to see if we can't figure out what those guys are. But let's go ahead and grab some data. It's one thing to have a hypothesis, which is lovely, and then it's another thing to actually make some data. So go ahead and do this. Here we go. So we're going to go ahead and take the data. So this is my goal. Let's see how this works. My goal is to use the mouse, which is here, obviously. I'm going to move the mouse down a little bit. Actually, I can move it down pretty far, because my goal is to start it here. I'll click it, and then what I'm going to do is I'm going to switch my hands. I'm going to move this hand back to here so I can stop it, and then I'm going to catch it before it crashes. I think that's what I want to do. I only want to collect data from when I let it go to when just before I stop it. I don't want to record the crash. If I record the crash, then that is going to be a different process. It's going to be cart moves under the influence of the fan, the push of the fan, and then it crashes. We'll need extra equations to describe that. All I want to do is collect data where it's fan is being pushed, or a fan is pushing cart. We measure it, speed up, and then we're going to stop watching it, and then I'll catch it. At least that's my goal. So let me go ahead and move this guy way over here to the start. Okay, so I'm going to press the start button. You can see that there. So what I've done is I'm going to press the start button, which I had a touch screen. I'm going to turn this on, and I'm going to go ahead and put my hand on it, and I'm going to go ahead and switch my fingers. Here we go. Wish me luck. I'm going to press start, and I'm going to switch. 3, 2, 1, go. All right. I didn't kill myself. It didn't die. And we're good. We got some pretty good data, actually, so we're going to take a look at this data. So now we actually have, we don't have to worry about guessing anymore, because we definitely have the data right there. We can see what happened. There we go. There's our prediction. 13, 14, 15. Okay. Wonderful. Sketch the actual shape of the position, velocity, and acceleration versus time graphs for the fan cart's motion. Okay, they're all versus time, which is what this guy is. Here's position. This is X. Again, I keep on catching myself calling it X, position, but it's position, X in meters. And then velocity is meters per second. And then acceleration is meters per second per second. So this is what it looks like. You'll notice that there is one data point that sort of drops right here. It looks like I caught it and it crashed into my hand right as I pressed stop. So when we go ahead and do this analysis, I'm not going to include this last point. Up here at the top, if I get my mouse back here, hopefully I don't get too... if I get my mouse back here and take a look at it, you'll see very, very closely there's two red dots that are the same. It doesn't come back down because it didn't jerk. This is where it was. This is really kind of smooth. It's fantastic. It really did slow down very quickly, and it really did change its acceleration, negative backwards. You can tell that it crashed in my hand and then went that way. I'm just not going to include that data. When we did our experiment last week, I mentioned if you make a mistake or if there's a goof, don't include the goof. And so I'm not going to include the goof. That was my goof. I should have stopped it before I hit that. That's fine. But if I take a look at it, it's kind of smooth all through here. That's kind of nice. This is kind of smooth. It sort of got bumpy there. There seems to be some bumps here. And the bumpiness that's in the middle is the same as the bumpiness that's in here. So it may be, looking at these little tiny tracks here, it could be that there's some dust inside there. Yeah, look at that. Gross. I'm going to go ahead and wash my hands. There was little tiny pieces of dust inside here, so maybe it was, sort of bumping and being bumpy down there. It's not very smooth. So yeah, as we walked through here, our data could tell that it wasn't being very smooth. That's it is what it is. And notice it's all going to average out anyway. But looking at this thing, down here or up here, the position versus time, it started at 0.4, which is where it was supposed to start, 0.4, and then it sort of did this. It sped up like a parabola. Again, that's what we were talking about with our ping pong ball. When we throw our ping pong ball, it slowed down at the top and then it speeds up. So what we're doing is, again, we're doing the down part. We're dropping it. Same thing here. We're doing the down part. So it speeds up. It's sort of the other half of the parabola. So that's why it's cool. It looks like that. Our velocity sure looks like a straight line that starts at 0. And our acceleration, if I go ahead and blow this up a little bit, I believe I can do that by doing this over here. There we go. That's it. Software is not amazingly too terrible. Again, there's a lot of noise here, but if I go ahead and look at it in the middle, you'll see that it really is just a straight line. So it looks like, with this fan on, it looks like the acceleration is constant. It's accelerating away from the sensor. The velocity is smoothly increasing. It's getting faster, 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 faster at a nice smooth slope, which means a constant acceleration. And overall, the position itself makes this swooping motion. It means starts slow and then gets faster as it goes. As we plot it out, it looks like that. Okay. So over here, what we're going to do is we're going to actually, rather than me just saying, oh, look, a nice parabola, oh, look, a nice straight line with slope, oh, look, a nice horizontal line, we're going to ask our mathematics friends to actually find an equation that best describes this data. Okay. So what we're going to do is we're going to fit all of these things with a polynomial fit. And again, I mentioned that we're not going to include this last data point. So let me go ahead and select the data for, no, I can't, I gotta start down here. I'm a goofball. Here we go. Just this data. There we go. I'm gonna go ahead and fit this to a polynomial fit, which is this guy. And if you look, it says if this were a ball, sort of upside down, it would fit this lovely parabola, which is lovely. And a parabola happens to give us these values. The values are values of the A term, the B term, the C term, and the D term. It's sort of like the quadratic equation, what is that? Negative b plus or minus the square root of b squared minus 4ac over 2a. Oh my gosh, I remembered that from junior high. That's what we mean by a's and b's and c's and d's. But for now, we're just going to read them off, and then when we come back into our conversation outside of lab, we'll talk about it. So for position versus time, this is 0.418. Now I know each of these happens to have an uncertainty or a standard deviation. You notice it's really kind of small. This e is the exponent on the scientific notation 10. So this is 4.6 times 10 to the minus 4. It's really small. This guy down here is times 10 to the minus 5. They're really kind of small. I'm not suggesting that we forget about them and they don't exist. It's just that it really is going to complicate our manual conversation and our calculations with our pen if we bring those along. So I'm just going to not record them. I'm not ignoring them. I'm not suggesting to somebody who's paid me to do this that we had perfect data. I'm just going to say, hey, you know what? They're not really important for our purposes. The B term is 0.0238. Double check it, 0.0238. 0.238, gotcha. This guy is 0.0507 or 07, wonderful. The D term is negative and it's small. Negative 9.03 times 10 to the negative 4. That's what that E negative 4 means, scientific notation. Okay, velocity, we're going to fit it to a polynomial as well. I'm only going to include the data that is not those last points, okay, up here at the beginning. Wonderful. I'm going to go over to the fit and do a polynomial fit again, and I'm also going to get this lovely thing, okay. It sort of looks like a straight line. There's the green thing, and I'm also going to get some terms for A, B, C, and D. So here we go. 0.0193, 0.110, a negative 0.00634, and a 4.52 times 10 to the negative 4. Fantastic. That's e to the negative 4. That's good. And then over here, I'm going to go ahead and grab these guys, not the last piece of data, and make sure they're all included.